In this video, we will present the fourth example scenario for the Smart Society programming framework. It assumes that the application receives a natural language description of a Java software artifact that the platform or application needs to produce for an external user. The software artifact is produced by a simplified two-stage methodology. The artifact is first coded by collective members invited to a joint repository, then verified against tests provided by another collective. The first phase is completed when a special tag is found in a commit, while the second when a certain code coverage is reached. Here on the left you can see the GitLab page of a group created for this demo. The application will take care of creating the required repository and adding members to it. On the right we have two consoles. The bottom one will run the programming framework runtime. The top one will be used for submitting commands to it. Our working directory is the scenario 4 folder in the project root directory. We will first set an environment variable with the GitLab API token that you can retrieve from the GitLab website. We will then take care of starting the runtime executing our application. We are using gradual run that will first compile then run scenario 4 main class. When the runtime is up, we will use a convenient script that we provide with the code for creating peers based on GitLab usernames. We are going to create 3 peers. As you can see, the 3 peers have been created using their corresponding GitLab numerical IDs. Now, with another provided script, we are going to submit the real task providing the group, the repository name, and a short natural language description of the task. The application takes care of creating the repository, since it was not already present, add the members to it, and performs a very straightforward negotiation where agreement is implicit. The first phase execution now starts. We can now check on the browser that the repository has been actually created and that the peers have been added as developers. The next step is to actually commit something. We have a very basic project that we are going to use. We first initialize the repository and then commit and push some few files as initial commit. We now add the source files and commit with a special string code complete between @characters to indicate the ending of the first phase. When this commit is pushed, we can see that reflected in the GitLab project activity page. In the bottom console instead, you can see that the task of the first phase has been completed and the execution of the second one is started by checking the code coverage. Now we are going to commit some tests, but we first comment most of them. We are also going to add the continuous integration scripts required by GitLab for building, executing the test, and computing the code coverage. Once the code has been pushed to the central repository, a new pipeline is started, sources are built, and tests are run. At the end of the build, the code coverage is computed. When the process is actually completed, we can see how the application can detect it. We are now going to commit all the tests that, as you can see, consist of calling the same method with different inputs. Let's now have a look to the tested method. This is just a huge switch over the tested inputs. When almost all the cases are tested, we reach enough coverage. Now that the last commit has been pushed, we just have to wait the running build to finish and see what it happens. The process is complete and we finally reached almost 97% of coverage, well above the required 90%. Once the application detects it, declares that the task is completed. We are now going to work through the scenario 4 code to understand the main structure. We will not anyway go into the details of how the system interacts with the GitLab API. In the main method, we first prepare the components that will be used by the runtime, such as the SmartCom communication middleware and the local peer manager implementation. Both are using a MongoDB instance that for convenience we are starting embedded. We then prepare the runtime using such components and specifying the class implementing the application interface that the runtime is expecting. When the runtime is started, it will enter in the main loop. To understand how the tasks are submitted, we can check how the SmartCom is instantiated. The callback for incoming messages is provided by the scenario for main class itself, and the messages are received by a REST input adapter. The callback accepts two kinds of messages, one for submitting tasks and the other for creating peers. The provided scripts we have shown running the ability of the application to create peers through SmartCom requests. The information is just a tool that we provide for convenience, but that does not make sense in the real case where the peers are independently registered in the peer manager. Let's see now how a task submission is handled. From the SmartCom message, we extract the content that we expect to be a JSON representation of the task, used for creating a task definition. Such definition will be then passed to the runtime in order to start the corresponding task. The interface between the runtime and the business logic is made by the application. We are going to explore how the application for this scenario has been implemented. The helper functions for creating the runtime takes care of initializing the application, calling the method init. This is how the application comes to know the actual Smart Society application context. In this case, we also register two kinds of collective-based tasks, one for the development phase and one for the testing phase. They are both on-demand collective-based tasks. In the first, we fix only the negotiation handler that should implicitly accept half of the members in the provisioning collective, while in the second phase, we both fix a provisioning handler simply returning the same collective it received as input and an implicit agreement for all the peers in the provisioned collective. The remaining handlers will be then provided only when information contained in the task request is available. The last method contained in this file, that is called createTaskRunner, is the one that will actually instantiate the class implementing the business logic, the TaskRunner. But first we can see how a task request for this scenario is created, starting from the provided task definition. The task definition consists only of a JSON object. From this object we extract the expected information such as the group and the project name, the GitLab token for interacting with the API, the natural language description, and the aimed code coverage ratio. We move now on the task runner that, as we said, dictates how the task is performed. The first step is to set up a query for retrieving peers with the field skill that corresponds to the skill provided by the task request. The query is then submitted to the peer manager in order to obtain the starting collective. The task runner then verifies the token provided in the task request that is used for accessing the GitLab API. Then the repository is created. It is now time to trigger the first phase. For doing this, collective-based task is required. It will be created based on the builder that has been registered during the initialization of the application. Now a provisioning handler is created that will take care of adding the members to the repository. The execution handler instead will take care of waiting for the expected tag in the commits messages. The collective-based task is run, and after the negotiation has been completed, the task runner will wait for the completion of the first phase. When this occurs, it is ready to go to the second phase. Here, the first step is to create a testing team collective obtained by removing from the original collective those that have been selected as developers by the negotiation phase in the previous step. This execution handler takes care of comparing the code coverage obtained by the test with the target one provided in the request. Once the collective-based task for the second phase has been set up and started, the task runner has only to wait for the final result.